Hello, my name is Helena, and today we will look at the difference in the nutrition of dogs and cats. I often hear from pet owners that cats happily eat dog food and vice versa. Or, what is even worse, that people feed their cats or dogs what they eat themselves. Sharing our homes for millennia, dogs and cats might seem like similar companions, yet they possess unique metabolic pathways that differ drastically from humans and each other. Understanding the distinct nutritional needs of our canine and feline companions is crucial for their health and well-being. Dietary distinctions between dogs and cats have been defined by thousands of years of unique evolutionary paths and domestication. So let's go back in time to understand their dietary strategies better. Dogs descended from social, pack-hunting wolves, Canis lupus, which had a flexible carnivorous diet. This ancestral feast-or-famine cycle, characterized by consuming large, infrequent meals after a successful hunt, led to adaptations for efficient nutrient storage and utilization, preparing them for the omnivorous shift. As opposed to dogs, cats originated from solitary hunters, Felis silvestris, adapted to catching multiple small prey throughout the day. This pattern resulted in a metabolism geared towards frequent, small, high-protein meals. There are also some differences in the domestication of dogs and cats that have shaped their nutritional needs. Dogs began their domestication journey approximately 33,000 to 16,000 years before the Common Era. By 50-100 years before the Common Era, they adapted to starch-rich diets, thriving alongside early human agricultural societies. This shift marked a significant dietary flexibility. Artificial selection has resulted in vast breed diversity in dogs, leading to variations in metabolism and feeding behaviors. Despite this, their fundamental omnivorous capacity remains. Cats were domesticated much more recently, around 7,500 years before the Common Era, primarily for pest control. Their domestication involved less dietary adaptation, meaning they retained a strong nutritional reliance on a carnivorous diet. Because the cat's primary function, pest control, did not require specialized anatomy, humans felt no need to alter their appearance. Most cats remained natural tabby-patterned animals. Intentional breeding for aesthetics only began in the late 19th century. Subscribe to uncover the secrets of cat domestication in future episodes. Canine and feline teeth are evolutionarily tailored to handle fundamentally different dietary profiles. Dogs possess relatively unspecialized teeth, a characteristic reflecting their omnivorous tendencies. While they retain sharp canines for tearing, their molars are flatter, designed for crushing and grinding a wider variety of foods, including plant matter. Cats are obligate carnivores, a fact profoundly evident in their highly specialized dentition. Their jaws are equipped with sharp, scissor-like teeth, perfectly adapted for shearing meat and crunching bone. They are not designed for grinding plant material. Both cats and dogs prefer food at temperature 30 to 38 degrees Celsius or 86 to 100 degrees Fahrenheit. This mimics the temperature of fresh prey and enhances the release of volatile aromatic compounds. While humans possess approximately 9,000 taste buds, dogs, 1,700, domestic carnivores such as cats only about 470 taste buds. While dogs possess nearly 4 times as many taste buds as cats, allowing for a more varied palate, the feline gustatory system is uniquely specialized for survival. Cats exhibit an exaggerated sensitivity to bitterness. This serves as a vital biological safeguard against the ingestion of toxins, though it presents a significant challenge in clinical pharmacology when administering bitter-tasting medications. Both species have a relatively low sensitivity to salt compared to humans and herbivores. Dogs have salt receptors, but they aren't very sensitive to the taste of salt on its own. Nevertheless, they show a strong preference for the salt-umami synergy prevalent in processed diets, which may predispose them to overconsumption if dietary intake is not strictly regulated. Cats are even less responsive to salt than dogs. They lack a strong salt appetite. In clinical terms, this means cats generally do not prefer salty flavors, and adding salt to their diet is rarely an effective way to increase palatability. Strict meat diet provides all necessary electrolytes. When a dog or cat consumes something salty, it triggers the water receptors on the tongue, which encourages the animal to drink immediately to maintain osmotic balance. High salt intake in dogs strongly activates the water units to prevent dehydration. Cats are less effective at compensating for excess salt through voluntary drinking. Due to their low thirst drive, domestic cats often need environmental enrichment strategies, such as water fountains, to stimulate drinking behavior and encourage hydration. Cats are unique in their complete insensitivity to sweet tastes. Felines have a defective mutation in the taste receptor type 1 member 2 gene. Since their diet consists almost exclusively of protein and fat, the evolutionary need to recognize carbohydrates has disappeared. Cats do not seek out or enjoy carbohydrates, sugars. Due to their evolutionary history as facultative carnivores, dogs have retained the ability to taste sweetness, facilitating the inclusion of fruits and berries in their diet. Cats are highly specialized in detecting nucleotides, such as adenosine triphosphate and inosine monophosphate, which act as markers for fresh animal tissue. While dogs also perceive umami flavors, their receptors are broader, allowing them to respond to a wider variety of amino acids, including those found in plant-based sources. Collectively, these dietary habits, dental structures, and unique taste perceptions enable dogs and cats to meet their specific macronutrient needs. In domestic cats, the activity of hepatic urea cycle enzymes, for example alanine aminotransferase and aspartate aminotransferase, is maintained at a high, constitutive level. They lack the ability to down-regulate these enzymes in response to low protein intake. Consequently, cats require from 30 to 50% of metabolizable energy from dietary protein to maintain nitrogen balance. Dogs exhibit metabolic flexibility, allowing them to adjust nitrogen catabolism according to protein availability. They can effectively conserve amino acids for structural maintenance rather than immediate oxidative energy. Unlike cats, the dietary protein maintenance requirement for dogs is significantly lower, ranging from 18 to 25% of metabolizable energy. Most animals, including dogs and humans, can create taurine inside their bodies from other amino acids. However, the cat is a biological exception. Nature decided that because cats eat mice and birds, which are naturally packed with taurine, they didn't need to waste energy making it themselves. Evolution essentially switched off the taurine factory in the cat's body. Consequently, cats are entirely dependent on dietary sources for taurine. In addition to their limited ability to synthesize taurine, cats deplete their internal stores much faster than other species. Cats require taurine to produce bile salts to digest fats. Unlike dogs, who can use glycine for this process, cats rely exclusively on taurine. Every time a cat eats, it depletes a portion of its taurine reserves. A taurine deficiency in cats causes progressive retinal degeneration. It begins as impaired night vision and culminates in total vision loss. Furthermore, taurine deficiency leads to myocardial dysfunction, typically manifesting as dilated cardiomyopathy, which can ultimately result in heart failure. The heart muscle becomes thin and flabby, like a stretched-out rubber band. It loses the power to pump blood, leading to lethargy and sudden death. Reproductive functions are also impaired. Mothers lacking taurine often suffer miscarriages, or their kittens are born with developmental defects and weak immune systems. Both species utilize fats as a primary energy-dense substrate. However, the feline requirement for animal-sourced fat is absolute due to their inability to synthesize arachidonic acid, that is an essential fatty acid. They lack the desaturase enzymes to synthesize it from linolenic acid, found in plant-based fats. Cats possess a high capacity for lipid oxidation but are prone to hepatic lipidosis during periods of negative energy. Dietary fat should account from 20 to 45% of metabolizable energy for cats. In dogs, fat serves as a major energy source during sustained physical activity, but they possess greater metabolic buffering against rapid lipid mobilization. They can synthesize arachidonic acid from linoleic acid, found in plants, making them less dependent on animal-sourced fats for this specific nutrient. Dietary fat should account for 10 to 25% of metabolizable energy for dogs. Cats are biological protein processing machines that constantly convert meat into blood sugar to maintain energy. They have significantly lower levels of pancreatic amylase and completely lack hepatic glucanase. This enzymatic profile means they cannot effectively manage a sugar rush, leading to prolonged hyperglycemia and an increased risk of diabetes. To prevent metabolic failure and diabetes, a cat's ideal carbohydrate intake should stay between 0 and 12% of metabolizable energy. During domestication, dogs developed multiple copies of the gene, which codes for pancreatic amylase. This allows them to digest and utilize complex carbohydrates, such as starch, very efficiently. This allows dogs to derive up to 30 to 60% of their energy from starch, utilizing it as a protein-sparing fuel. There are significant disparities between dogs and cats regarding the absorption and metabolism of certain vitamins. Dogs efficiently convert plant-based beta-carotene into active retinol within the intestinal mucosa, a process catalyzed by the enzyme beta-carotene dioxygenase. Cats lack the intestinal enzyme beta-carotene dioxygenase and cannot convert plant-based carotenoids into active vitamin A. They require preformed vitamin A, retinol, found exclusively in animal tissues. In cats, vitamin A deficiency triggers progressive ocular damage, starting with impaired night vision. Additionally, it causes reproductive failure and skeletal malformations. Although in practice we more often encounter excess vitamin A in cats, subscribe to explore these topics further in our upcoming videos. Like humans, dogs can synthesize niacin from the amino acid tryptophan. Cats have all the necessary enzymes, but the activity of picolinic acid carboxylase is so high that it diverts tryptophan toward the production of picolinic acid and acetylcoenzyme A, rather than niacin. So, cats have a dietary requirement for niacin that is roughly 4 times higher than that of dogs. Because niacin is essential for energy metabolism, a deficiency in cats leads to rapid weight loss, oral ulcerations, and severe gastrointestinal distress. Feline liver enzymes are constitutively active and cannot be downregulated. Since vitamin B6 is a mandatory cofactor for protein metabolism and gluconeogenesis, cats deplete their B6 stores much faster than dogs due to intense nitrogen turnover. Due to their high nitrogen turnover, cats require significantly higher levels of dietary pyridoxine than dogs to prevent metabolic deficiency. Thank you for watching. I hope this video gives you a better understanding of the nutritional needs of dogs and cats.